My name is Amanda Kerr, and this is my FE problem presentation for CEE300 Engineering Business Practices. So today, I'll be presenting about compound interest. So one of the things that makes compound interest so valuable is that it demonstrates exponential growth, due to the fact that the interest is calculated on increasing amounts. So as you can see, as the time increases, so does the value. But unlike simple interest, which is linear, it grows in an exponential pattern. So initially, the value is increasing by really small amounts. But as time increases, the value increases in larger increments. So, like I was saying before, compound interest is different than simple interest because in simple interest, the interest isn't actually added to the principal. And so no compounding occurs. The value just keeps increasing by the same amount. It's a linear graph. But in compound interest, as you can see, it has the exponential term. So the amount of the interest that you pay into the principal adds to the amount that keeps getting increased over time. So eventually it'll increase much quicker, whereas simple just increases the same amount the whole time. Compound interest is used a lot more frequently in the real world, in economics and finance, so it's definitely a better option to explain because it's really valuable to understand. So, most people will experience some type of compound interest at some point in their life, and one really good example of that is APR, which is the annual percentage rate. And you'll usually see this in, credit card rates, mortgages, loans, and so definitely a good idea to have a basic understanding of it. So, to help with your basic understanding of compound interest, I'm just going to go over what the variables mean within the formula. So A is your value after T periods, where P is your principal amount, which is actually your initial investment. So, pardon my handwriting. R is your interest rate, but it actually needs to be in decimal form. So I'm going to write that down because if you put it in percentage form, it's not going to work. N is your number of compounding periods. And so that has to be per year, and that's also really important. And then T, as I just said, needs to be time also in years. So the reason that I'm super annoying about saying all of the years and decimal year is that everyone, no matter what level of student or computation you're doing, makes issues with the units, and that can cause problems with all of your calculations. And it's really annoying when you get to your final point and all of your math is technically correct, but your units don't match up and so your answer's wrong. So let's go to an actual problem just to show an example of how compound interest works with computation. And the start of this actual problem is that coffee is not cheap, and that's the basis of this problem. It's an issue very near and dear to many college students. So, let's just go into the situation. In the first 5 years after graduating, you work at a really stressful job, and you drink a giant cup of coffee 7 days a week, 365 days a year. So assuming that you burn out from this job after 5 years, and then you work for the government or something, how much more could you have earned by the end of your career if you had instead put the money that you had spent during those 5 years on coffee into an account that is compounded monthly with 3% interest, assuming that you officially retire about 40 years after burning out? Okay, so for the purposes of solving this problem, we're going to have to assume that coffee's expensive. Let's say that it's about $5 a cup. We're also going to assume, just to simplify the problem, that over the course of 5 years, there's no inflation in the price of the coffee. So it'll just stay $5 for the whole time, which isn't realistic, but it'll help us here. And then 3, that frequent customer discounts are going to be insignificant. So the first math step is going to be to assign the variables. So A is going to be the amount of money that could have been earned after 40 years. P is an interesting step. So like I said, it's the amount of money that you could have earned after 5 years of buying coffee. So we're just going to treat that as a lump sum. And so you solve for P. And that's going to be $5 a day, 365 days a year, for 5 years. And that's going to give you around $9,000, but in your calculator it'll give you $9,125 total. So we're just going to put that here. R, like I mentioned before, is going to be 3%, so in decimal form that's 0.03. N, because it's a monthly compounding period, is going to be 12 for 12 months a year. And then T is going to be the amount of time that that money is in an account, so that's going to be 40 years. So now, if we plug in the values, we have A is equal to 9,125 times the quantity 1 plus 0.03 over 12, all raised to the power of 12 times 40. So if you put that into your calculator, you get that it's about $35,000, or $35,139.76 to be exact. So, in conclusion, the amount of money that you spent on coffee in 5 years could have earned you $35,000 in a bank with these conditions for compounding. So, probably a good thing to think about when you're going to Starbucks every day.